Do you have any questions that I can try to answer related to mini project 1, which I tried to walk through in great detail last week, or anything else that I can try to answer?
I don't think I have any questions.
I don't think I have any questions either.
Okay, thank you, Keyshawn. Okay, today's topic, and let me share my screen. It is Monday, March the 13th. I do believe IT has helped me and has resolved the mini tab access issues. So all of you should have access now. The 4 of you that are present have indicated that you're okay, that you do have access. The deadline for quiz 2 was extended because you needed mini tab to do it. And it is now due by Wednesday, March the 15th of 2023. And then mini project 1 is due by Friday, March the 17th. Today, we're going to talk about, begin an overview of probability distributions, and then talk specifically about discrete probability distributions. Depending on how recent you've taken Stat 1401, you may remember some of this information. Some of it may be new information, especially if it's been a while since you took Stat 1401, since some of this content was more recently added to the course. So if you are navigating the course, we are still in Module 1, and the lesson title in the course is Random Variables. Okay, it's called Random Variables. And you'll see on that page when it opens up, it's taking its little time this morning, the PowerPoints and the materials that you have access to for this particular topic. It's just taking its lovely time to load this morning.
I know it happens on my computer, so
Yeah.
I know it sucks.
Okay, so there is a video if you prefer to watch it, but I'm going to walk through the overview of probability distributions. And then you have the PowerPoint for that overview. You have discrete probability distributions and continuous probability distributions. There's some flow charts that can walk you through how to do the problems. We will be using Minitab for the binomial distribution. There's a video there, and then you have quiz 3. Quiz 3, I don't believe, is due until next Sunday. So I'm going to begin with the overview of probability distributions. We really are going to spend a significant amount of time from now till the end of the term looking at various probability distributions in various formats. So this is kind of a important topic within the course. So we really have to begin with, what in the world is a probability distribution? So it really relates back to something that we briefly talked about, or something that you learned in Stat 1401 called a frequency distribution. Excuse me. A frequency distribution allows us to take our data and organize it into a table form. They can be a jump start to the various graphs that we create, whether we're creating a bar graph or a pie chart or a histogram or a stem and leaf plot. I always think about a frequency distribution shows us what really actually happened. So a frequency distribution is our reality. It's what really happened when I collected the data. A probability distribution describes or identifies what will probably happen, what should happen based on an assigned probability for every possible outcome. Okay, so a frequency distribution is like your reality. Probability distribution is more of a theoretical model. It tells us what should happen if everything was working the way it's supposed to. Now, we all know in reality, everything doesn't work the way it's supposed to. So the probability distribution creates for us this theoretical model. A probability distribution can be displayed as a table, as a graph, or even just a formula. Now, our primary focus is going to be on table form and graph form, but it could also be in a formula form if we needed it to be that way. So here's kind of an example of how the two pieces fit together. So if our event or our experiment is that we're going to roll a die, a six-sided cube, a frequency distribution would show us exactly how many times we rolled a 1, how many times we rolled a 2, a 3, a 4, a 5, or a 6. It would actually show us what actually happened when I rolled that die. We can then also calculate the mean and the standard deviation for that frequency distribution. We know, we talked briefly about probability. We know that probability for each outcome is 1 out of 6, because there's one way to roll a 1 out of 6 options. For the probability of 2, there is one way to roll a 2 out of a 6. And we put those two ideas together to create a theoretical model that if we should expect to roll a 1 1/6 of the time. We should expect, in theory, to roll a 2 1/6 of the time. And then also we can learn, and we're going to look at how to do that a little bit later today, how to calculate the mean and the standard deviation for that theoretical model. So again, we're taking kind of two concepts that you've previously learned and putting them together to create a theoretical model, which we refer to as a probability distribution. So why do we even need a probability distribution? Why do we care what could theoretically or possibly happen? Well, guys, a lot of decisions that you make in business, in insurance, and really other real life related situations are made by assigning probabilities to all the possible outcomes pertaining to the situation and then evaluating those results. For example, a saleswoman can compute the probability that she'll make 0, 1, 2, or 3 or more sales in a single day. Based on her past experience and that sort of thing, she can predict, looking at patterns within her sales, how many sales she's going to make on a single day, which would then allow her to calculate the average number of sales she makes in a week. And if she's working on commission, she's able to approximate her weekly outcome. Insurance companies often assign probabilities to life expectancies. How long do they think you're going to live? And based on those probabilities, that's how they set the insurance rates for life insurance. Even things like car insurance, they look at your age, your driving record, and those sort of things, and they assign a probability that you're going to have an accident or probability that you're going to need to utilize that insurance. And again, they determine at that point what your insurance rate or price is going to be. So there's lots of uses for probability distributions in the real world. There are two categories of probability distributions, and hopefully these categories sound familiar. You have discrete probability distributions, and then we also have continuous. Discrete and continuous, if you'll remember, were the two categories of data. We had quantitative, discrete, and quantitative continuous data. Similarly, we have a discrete probability distribution, or we could have a continuous probability distribution. Okay. With discrete has a countable number of possible outcomes. Again, think about the example of rolling the die. There are 6 possible outcomes when we roll a die. Flipping a coin, there are 2 possible outcomes when we flip a coin. So a discrete probability distribution has a countable number of possible outcomes, and most often is going to involve whole units. Okay, very rarely in a discrete are you going to have fractional units. The probabilities for a discrete probability distribution are determined theoretically or possibly via observation. Okay, meaning where you actually perform the experiment a number of times, or you look back at patterns over a period of time. We typically display a discrete probability distribution either using a table or a graph. And there are 2 requirements for a table or a graph to be considered a discrete probability distribution. The first one is that the sum of the probabilities in the sample space. If we take all of the different things that could happen and we add up the probabilities must total to 1. The probability of each outcome, each individual outcome, must be between or equal to 0 and 1. Okay. Now, let me go on to continuous, and then I kind of got a little bit ahead of myself, and I want to go back and review a couple of things. But a continuous probability distribution has an infinite number of outcomes between any 2 values on an interval. Remember, with a continuous variable, we could break it down into smaller and smaller units. We typically could have fractional or decimal portions. So it's the same idea with a continuous probability distribution. You have to kind of fill in the gaps between, say, 0 and 1. There's no gaps, and you could be in any space or value between 0 and 1. For continuous probability, the probabilities are determined theoretically. Again, we can display them in a table or a graph. And the 2 requirements are very similar, but instead of looking at it from a algebra standpoint, we look at it more from a graphical standpoint. And so we talk about the area under the curve. And so the total area under the curve for a continuous probability distribution is 1, and the probability of each outcome is between or equal to 0 and 1. We're going to talk about 2 specific types of discrete probability distributions. They're not the only 2 that exist. Some of the various forms or the various types of discrete probability distributions are: you have just a general type, broad spectrum probability distribution. You have a binomial. There's one called Poisson, and there's also one called a hypergeometric. Guys, you can take an entire 15-week course or a condensed 8-week course on discrete probability distributions, and you would talk about all the different types. Our focus in this course are on the two that are probably used the most often, which are the general and the binomial. We also will talk about continuous probability distributions. And again, you can take an entire course on continuous probability distributions. And there are a variety of those that we're going to talk about even throughout the rest of the course. We have the uniform distribution, exponential distribution, the normal distribution, which is one of the most powerful and most used continuous probability distributions in all of statistics, the student's t-distribution, chi-square, and the f distribution. So we're going to be talking a little bit about each one of those as we proceed throughout the rest of the course. Now, I did get ahead of myself just a wee bit. I jumped straight into probability distributions, but we probably should have talked briefly about probability before we jumped into that discussion of probability distributions. So I want to review real quickly. I want to backtrack just a minute and review real quickly with you the 4 basic rules of probability. Okay. So I want to review the 4 basic rules of probability with you. We really kind of have touched on them already, but I want to make sure that you understand what they are. Okay, so probability is the chance that a particular event occurs. Again, if you think about the idea of flipping a coin, if our experiment is that we're going to flip a coin, then I could ask, what's the chance? What's the probability that I flip a head when I flip that coin? Okay, so the notation for that, the way you'll see it, we usually see the capital letter P, parentheses, and then maybe the word head or a symbol. That notation there means what is the probability of getting ahead when I flip a coin. Okay, it's a kind of a shorthand notation that's used. Okay, so let me kind of give you some pointers here. The P, hopefully it's obvious, stands for probability. The word or symbol inside the parentheses is your event of interest. Okay, it's what you want. The parentheses here are simply being used as separation symbols to separate the letter P from that event of interest. Okay, they in no way, shape, form, or fashion imply multiplication. Most probabilities, when we think about it from a theoretical perspective, and there are various ways to calculate probabilities. Okay, depending upon your situation. But in most cases, when you think about calculating the probability of a particular event, we think about the number of ways the event can occur over the total number of possible events. Again, if you relate that back to the idea of flipping the coin, okay, and we are interested in the probability of a head, specifically, then I want to know the number of ways to flip a head, which hopefully we all know is there's one way to get a head on a coin, excuse me, over the total number of possible options. Well, when I flip a coin, there's only two options. So the probability of a head would be 1 out of 2, or 0.5, or 50%. Probabilities can be written as fractions, decimals, or percents. Now, there are about 4 rules that kind of govern the world of probability. And even when we're talking about discrete and continuous probability distributions, we have to utilize these 4 rules. So I want to outline those 4 rules for you. Okay, so rule number 1, or guideline number 1, whatever you want to call it, rule 1 says all probabilities are between 0 and 1. That means 2 things, or there's 2 consequences related to that rule. First of all, probabilities are never negative. So for some reason, and you're doing the calculations and you get a negative number, hopefully there's a big red flag waving at you, because you should not have a negative probability. Secondly, probabilities are never greater than 1 or 100%. Now, we like to talk about things being over 100%. Like we like to say, like, oh man, he gave 110% out there today. Statistically, you cannot have more than 100%. So all probabilities are between 0 and 1. They will never be negative, and they will never be greater than 1. So if you have either of those things occur, then you should have a big red flag flapping in the wind going, woo, woo, I've made a mistake. Because probabilities will never be negative, and they will never be greater than 1. Rule 2, the probability of an impossible event is 0. Meaning if there's no way, no how that that event is going to occur, regardless of what you do, if there's no way, no how that that event is going to occur, its probability is 0. 0 means it is impossible. In symbols, the probability of an impossible event is 0. For example, if I say, what's the probability that you're going to roll a 7 on a die? We just talked about a die a minute ago. A die is a 6-sided cube that is numbered 1 through 6. There is no way, no matter what you do, if you roll a single die, that you're ever going to roll a 7. So the probability would be 0. Probability that Thanksgiving is on a Sunday. Well, if you know anything about the calendar, at least the calendar that we use within the United States, Thanksgiving is always on a Thursday, meaning it will never, ever be on a Sunday. So the probability that Thanksgiving's on a Sunday is 0. Rule number 3 says the probability of a certain, or if you want to think about it as absolute event, is 1. This is the other extreme. Okay, the probability that the event is certain it's going to happen regardless of what you do is 1. So the probability of a certain event is 1, meaning regardless of what you do, no way, no how is that particular event going to occur. So again, thinking about some examples. If I say, what's the probability you roll a number less than 7 on a die? Well, there again, all the numbers on a die are less than 7. 1, 2, 3, 4, 5, or 6. So that I'm always going to get a number less than 7. So the probability is 1. If I say, what's the probability that Easter is on a Sunday? There again, if you're familiar with the calendar that we use within the United States, Easter is always and forever on a Sunday. So when you're thinking about probabilities, okay, it's like you have this scale, okay? And let me make some more space here. Okay, so think about this. We know that all probabilities are between 0 and 1. 0 means the event is impossible. No way, no how is it happening. 1 means the event is certain. It's definitely, without a doubt, going to happen. And then I can have any value in between that. So if we think about it, halfway would be our 0.5 or 1/2 or our 50-50 mark. And so we can have any decimal value in between. So thinking about that as a scale, as you move from the impossible, you know, if you're close to zero, your event is less likely if you're close to zero. But as you move away from zero and move towards one, your event becomes more likely. So we move from being less likely to more likely. The closer you are to one, the more likely the event is to occur. So you can think about it as a graduated scale, like sort of like a thermometer. The closer you are to zero, the less likely it is to occur. The closer you are to one, the more likely it is to occur. The last rule says the sum of the probabilities for all the possible options is 1. Now remember, the word sum means to add or to total. So if I total up all of the possible things that could happen for a particular event, they have to total to 1, because 1 implies something's going to happen. Think about the idea of flipping a coin. Again, we know when we flip a coin that we're either going to get a head or we're going to get a tail. Probability of a head would be 1 out of 2. Probability of a tail is 1 out of 2. Those are the only two things that can happen. So 1/2 plus 1/2 is 1/2. Meaning something's going to happen when I flip that coin. And you really need to keep those rules in your head as we're working through the information related to the probability distributions. Let me go back for a minute to this idea of probability distributions. Notice for the discrete, I actually said 2 of the rules that apply to probability in general also apply to a discrete probability distribution. All of the probabilities have to be between 0 and 1. That's rule 1. And the sum of the probabilities in the sample space, meaning all the possible options, has to total to 1. That's rule 4. So again, you've got to kind of keep those rules and guidelines in your head. The rules actually exist for the continuous as well, but again, we think about it more from a visual or a graphical perspective. Okay, and so again, we still say the probability of each outcome is between 0 and 1, which visually means there's going to be a bar there. Okay, and then we refer to the area under the curve as 1, and I'm going to show you probably on Wednesday that relationship between probability and the area. There is a direct relationship there. And we'll talk about it when we begin to talk about continuous probability distributions. Okay, so let me pause for a moment and see if you have questions about probability in general or about the overview of a probability distribution. The next thing we're going to do is get into a specific type of probability distribution. We're going to specifically talk about discrete. So do you have questions before we continue?
No, I don't have any questions.
Not me either.
Okay. Thank you all. So now we're going to move specifically to discrete probability distributions. And we're going to look at two of the different types of discrete probability distributions. Okay. Our first focus is going to be just on kind of a general, broad, across the board, discrete probability distribution. So by the end of this lesson, you want to be able to recognize and understand discrete probability distribution functions to determine if a given scenario represents a discrete probability distribution, and then to be able to calculate the mean and the standard deviation of that discrete probability distribution. To calculate and interpret expected values. And then we'll do the same thing specifically related to a binomial distribution. Okay, so let me remind you, we just talked about it, but I want to remind you about discrete probability distributions. They have a countable number of possible outcomes. Again, flipping a coin, you have 2 possible outcomes. Rolling a die, you have 6 possible outcomes. Answering a multiple choice question on a test. Maybe you have 5 choices, A, B, C, D, E. Answering a true false question, you would have true or false. So you have 2 possible outcomes. So you have a countable number of possible outcomes. Again, we can display them in a table or a graph. Usually for discrete, we display them more so as a table. We usually use graphs more so with continuous. So for discrete, is primarily a table. Again, the probabilities are determined theoretically or possibly by observation. And again, the 2 primary requirements are that the probability of each event or each outcome has to be between 0 and 1. Probability should never be negative, and it should never be greater than 1. And then secondly, if you look at all of the options, the sum of the probabilities in the sample space are equal to 1. Now we're going to utilize these 2 requirements. If those are the 2 requirements to have a discrete probability distribution, then my first decision is going to have to be, do I have a probability distribution? Are all of my probabilities between 0 and 1, and do all of the probabilities add to a total of 1? Okay, so we're going to use that in just a minute. I'm going to give you the formulas for the mean and the standard deviation for a general probability distribution. Now, these problems in terms of finding the mean and the standard deviation is a hand calculation using a calculator. A general discrete probability distribution is not something we will do in Minitab. You will need a handheld calculator to perform these calculations. And I've given you the formula, and then I've tried to write out in words what you're supposed to do. To find the mean, we multiply each x times its probability, and then we add those values up. The standard deviation is a little bit more complicated. We subtract the mean from each x, square the answer, multiply it times its probability, and then add the results. and we ultimately do have to take the square root. And I'm going to demonstrate that in some examples in a minute, but those are the two formulas. Guys, for the midterm, you will be able to use one 8.5 by 11 sheet of paper with notes on it front and back. Now, I remind you and provide a list of things that you should probably put on that note sheet, but definitely you're going to want to have these formulas. I don't need you to memorize the formulas. I need you to know when to use and apply them. Okay, so you'll be able to have the formulas on your note sheet for the midterm. You simply need to know how to use it appropriately. And I'm going to demonstrate that in just a minute. So let's jump in to some examples. Again, with the discrete probability distribution in its general form. Okay. You have to do this by hand. And I moved these questions over to the Word document so that I could make notes for you a little bit easier than I can on the PowerPoint. Okay, so the question here is, let me make a note here. Does this probability distribution or table represent, I should say it this way, does this table represent a probability distribution? Okay, that's our question. Does the table represent a probability distribution? Now it tells me what this table represents. So let's kind of learn about what information we have here. Let me make this bigger where you guys can see it. Okay, a hospital researcher is interested in the number of times the average post-op patient will ring the nurse during a 12-hour shift. So somebody's had surgery, they're still in the hospital, and we're counting the number of times that they would ring the nurse over a 12-hour shift. For a random sample of 50 patients, the following information was obtained. The X, our variable, is the number of times a patient rings for the nurse in a 12-hour shift. And so we have the options. They ring 0, 1, 2, 3, 4, or 5 times. That's the X. The second column is the probability. And these probabilities are probably based on, collecting the numbers over a long period of time. So it's basically collected by observation. I don't really have to know how they're collected or how they arrived at these numbers. But what I do want to know is this a probability distribution? So to decide if this table is a probability distribution, you have to verify or confirm that we meet the two conditions. Okay, does this table meet the two requirements? The first requirement is that all of your probabilities are between 0 and 1. And then the second requirement is that the probabilities add or total to 1. So if I look at the first requirement, I can scan down the probabilities. 0.08, 0.16, 0.32, 0.28, 0.12, 0.04. All of those are values between 0 and 1. None of these values are negative. None of them are over from 1. So this is met. I can check that off. All of the probabilities are between 0 and 1. You're just scanning down the column. Then the second one maybe is going to require a little bit more effort because I need to see if these probabilities total to 1. So I'm going to take my calculator and I'm going to add these values together. We're going to add the values using our calculator. Okay, so I've got my calculator and I'm going to add those numbers up. 0.08 plus 0.16 plus 0.32 plus 0.28 plus 0.12 plus 0.04. And when I add them up, I do get a value of exactly 1. So again, I have met, or I meet, the second requirement, which means, yes, this table is a probability distribution because both of the requirements are met. Yes, this is a discrete probability distribution. Now, guys, don't overthink it. Again, you're just confirming that this table meets both of those requirements. If it does not, then it's not a discrete probability distribution. Okay, so I know that I have a discrete probability distribution. Questions? Okay, let's look at another one. It says a company wants to evaluate its attrition rate. In other words, how long new hires stay with the company. Over the years, they have established the following probability distribution, where X is the number of years a new hire will stay with the company. And it looks like we have the options 0, 1, 2, 3, 4, 5, or 6. And the probability, or P of X, is the probability that a new hire will stay with the company X years. Now, again, it tells us here that we have this probability distribution, but I don't necessarily want to just trust what they're telling me. So I want to first verify. Okay, so I want to verify that all of my probabilities are between 0 and 1. Well, as I'm looking down through there, 0.12, 0.18, 0.30, 0.15, I don't have the value for 4 years, 0.10 and 0.05. So I'm not quite sure yet. I also know that the probabilities have to total to 1. But again, I don't know the probability for 4. But I do have enough information that I could find the probability of 4, which is really the first question that I'm asked. They want me to find the probability that X equals 4. Okay, so we know that this probability has to total to 1. So if I know it has to total to 1, I can take 1 and subtract all the other probabilities. if I know what all these others are, whatever's left has to be the value for 4. So if I can add all these others up, okay, and then I'm going to subtract from 1 because it has to total to 1. That's the requirement. So I'm going to use my calculator and I'm going to add those values up first. 0.12 plus 0.18 plus 0.3 plus 0.15 plus 0.10 plus 0.05. That gives me a value of 9/10. So I have 1 minus 0.9. Well, 1 whole minus 0.9 leaves me with 0.1 or 0.10. So the value for 4 would be 0.10. Again, they tell me in the beginning it is a probability distribution. So I can apply the requirements. All the probabilities have to be between 0 and 1. I know them all but what the value is for 4. I can use the fact that they have to total to 1 to find that missing piece. It's kind of like doing an algebra problem or finding that last puzzle piece. So the probability of 4 is 0.10. I can then see all of my probabilities are between 0 and 1, and they do now total to 1. I can also be asked other questions about this particular probability distribution. Now I'm going to put in my 0.10 here because we already know it's 0.10. I could be asked, what's the probability that a new hire stays longer than or equal to 5? This is the probability that X is greater than or equal to 5. Meaning, what's the probability the new hire stays 5 years or more? Okay, so you need to think about what this symbol means. In this context, greater than or equal to would imply that the new hire stays 5 or more years. Remember that symbol is greater than or equal to. So think about what that would mean. If I want to be greater than or equal to, that really means it could be the probability that he stayed exactly 5 or the probability that he stayed 6. In probability theory, the word or means to add. So if I add together the probability of 5 and the probability of 6, that's going to tell me the probability that a new hire stays 5 or more. We're just interpreting the symbols. So I would have 0.10 plus 0.05. I'm just reading those numbers directly off of this table. And I'm going to add them together. And I get 0.15. So the probability that a new hire stays 5 or more years is 0.15 or about 15%. Again, don't try to overthink it, but pay attention to the symbols and the words and think through what it means. Okay, let's look at another one. The next one is probability X is less than 4. Okay, so this time you have the less than symbol. In this context, that means what's the probability a new hire stays less than 4 years. Now, guys, be careful here. That does not include 4. There's not an equal bar there. It is less than. So if it is less than, and let me put my value in there again. Okay, if it is less than 4, I'm looking at, it could be 0 or 1 or 2 or 3, but not 4. The 4 is not included. Again, or in terms of probability means to add. So I want to add these probabilities together. So I would have 0.12 plus 0.18 plus 0.30 plus 0.15. I'm going to add those together. Again, use your calculator. Okay. 0.12 plus 0.18 plus 0.30 plus 0.15 gives me 0.75. So the probability that a new hire would stay less than 4 years is about 0.75 or 75%. Okay, then it says on average, make the words bigger. On average, how long would you expect a new hire to stay with the company? And then it asks, what is the standard deviation? And let me put in my 0.10. Okay, so maybe in a little indirect way, this first question says on average, okay, which means they're asking you to find the mean of the probability distribution. And then the second question is pretty straightforward. It says, what is the standard deviation? Okay. So for the mean, okay, the formula for the mean is you take each X, multiply it times its probability, and then add them up. So I'm going to make another little column here. Probably need to make it a little bit bigger. Hold on just a second. I'm going to add a column to my table. And I'm going to multiply the X times P of X. And I'm going to write it out for you. Okay, so I would have 0 times 0.12, which is 0. 1 times 0.18, which is 0.18. 2 times 0.30, which is 0.60. 3 times 0.15 is 0.45. 4 times 0.10 is 0.40. 5 times 0.10 is 0.50. And 6 times 0.05 is 0.30. Now, I did all that in my head. Guys, if you can't multiply that, the X times the P of X in your head, please get the calculator. Okay, but we take each X, multiply it times its probability, and get our answers. And then we total those answers up. Okay, so I'm going to add these values up. So again, I'm going to use my calculator to do so. I have 0 plus 0.18 plus 0.60 plus 0.45 plus 0.40 plus 0.50 plus 0.30. And I get a value of 2.43. So my mean is 2.43. Now you have to have the mean, so you need to calculate it first because you have to have the mean to calculate the standard deviation. Now the standard deviation is a little bit more involved, and let me see if I can copy this table again. I don't want the whole thing, so let me go up here and get the other one. Okay, any questions on the mean before I do the standard deviation? Okay, the formula for the standard deviation is the square root of the sum of x minus the mean squared times the probability of x. Okay, so I'm going to add a couple of columns here. Whoops. Kind of crooked there. This is the easiest way to do it, okay? So I'm going to break this down into steps, okay? The first step is we have to take each x and subtract the mean that we just calculated. Okay, so I would have 0 minus 2.43 is negative 2.43. 1 minus 2.43 is going to be negative 1.43. Again, I'm doing it in my head. You can get a calculator. 2 minus 2.43 would be negative 0.43. 3 minus 2.43, and I'm going to get my calculator for that one. 3 minus 2.43 is 0.57. 4 minus 2.43 is 1.57. 5 minus 2.43 is 2.57. And then 6 minus 2.43 would be 3.57. Okay, so I take each x and subtract the mean. The mean that we calculated was 2.43. That's why I'm using 2.43. Once you've performed the subtraction, then I take that answer and I'm going to square it. Okay, so I take this answer and I square it. So I'm going to have negative 2.43 squared. And I'm sorry, I can't do that in my head. That gives me 5.9049. Then I'm going to do negative 1.43 squared. That is 2.0449. Negative 0.43 squared is 0.1849. 0.57 squared is 0.3249. 1.57 squared is 2.4649. 2.57 squared is 6.6049. And then lastly, 3.57 squared is 12.7449. Once you have it squared, the third step is to take that answer and multiply it times the probability. Okay, so I'm going to take 5.9049 times 0.12. I'm going to write all these out. 2.0449 times 0.18. 0.1849 times 0.30. 0.3249 times 0.15. 2.4649 times 0.10. 6.6049 times 0.10, and 12.7449 times 0.05. It's a process. Okay, so then I'm going to do those multiplications. You can use your calculator. Now, what you could do is type it all into your calculator, because after you get them multiplied, you want to add them together. So you could do that step if you wanted to at the same time. Okay, I'm trying to get the numbers multiplied out for you. This is probably the longest process you'll have for this particular topic. All right, then the next step, after you get that multiplied out, the next step is to add these up. So I'm going to take these numbers and add them up. All right, so I have 0.708588 plus 0.368082 plus 0.05547 plus 0.048735 plus 0.24649 plus 0.66049 plus 0.637245, and I add them up. And when I get them added up, I have 2.7251, and that is the value that's under the square root. And so the last step to get to my final answer is to take the square root of that number. And when I take the square root of 2.7251, I get that my standard deviation is 1.6507. It keeps going. Usually you're asked to round to 2 places. So we would say my standard deviation is 1.65. Guys, there's no other way to find it. You have to go through those steps. Do you have a question about the steps?
No, I don't have any questions.
Not me either, but it is long.
It is long. It is long. So, you know, and if you once you get comfortable with it, you can combine some of the steps in your calculator, but just be careful.
Okay.
Okay, questions related to kind of the generic probability distribution. Okay, I'm going to move then to the binomial. Because probably more so, I mean, the general, it's good to know about the general discrete probability distribution. But again, probably the one that you're going to encounter more often is going to be the binomial. Of the ones that I mentioned earlier today, the general, the binomial, the Poisson, and the hypergeometric, probably the binomial is the one that you will see used the most often. Okay, so let's talk about the binomial for a minute. It is still a discrete probability distribution, which means I still have a countable number of outcomes. It's usually displayed as a table. All of the probabilities are between 0 and 1, and the sum of all of the possible outcomes is 1. Okay, those guidelines, those rules have not changed. If you think about the word binomial, the prefix bi means 2. And so a binomial experiment, which ultimately leads to a binomial probability distribution, has 2 outcomes. It's an event that has 2 outcomes, or we can reduce it or force it to have 2 outcomes. Again, some examples. Toss a coin, heads or tails. A baby is born, biologically, boy or girl. Any kind of sports game, you have win, loss. You can have quiz questions, true, false. A medical treatment, effective, ineffective. Blood pressure, normal, abnormal. Rolling a die, we can force to have 2 outcomes because we can say, I want to get a 5, and then we lump everything else together as not being a 5. So you can think about it as you get what you want, a success or a failure. So 5 and not 5. Even with a multiple choice question that has maybe 4 or 5 options, you can force it into correct and incorrect, right and wrong. So a binomial experiment, which leads to a binomial probability distribution, has 2 outcomes, or we can force it to be 2 outcomes. To be a binomial experiment, again, which leads to the binomial probability distribution, there are 4 requirements. The first requirement is that you have a fixed number of trials. You're going to tell me, we're going to flip that coin 20 times, or we're going to roll the die 50 times. Okay, you have a fixed number of trials. You know how many times you're going to do it. Each trial can have only 2 outcomes or be reduced to 2 outcomes. Again, we think about it in terms of success and failure. Success is you get what you want, and it is represented by a lowercase p, think probability. Failure is you don't get what you want, and it's usually represented by the letter Q. And Q is equal to 1 minus P, because P is success, Q is failure. When you add the two together, it has to total to 1. The outcomes of each trial must be independent of each other, meaning what happens when you flip the coin the first time does not affect what happens the second time, does not affect what happens the third time. They're independent of each other. One does not affect the other. Fourth condition is the probability of success must remain the same for each trial. You're flipping the same coin every time. Okay, you're not changing the coin, or you're rolling the same die. And we'll walk through these again in a minute, because again, we want to verify that we have a binomial distribution. For the binomial probability distribution, we do have a formula that allows us to calculate it, but it is super, super messy. And so we don't usually use it. We're going to let Minitab do these calculations for us. One of the issues with the formula is it only allows us to figure exactly X successes. So if I'm going to flip the coin 20 times, I could find the probability that I get exactly 7 heads. But if I wanted to find the probability that I get less than 7 heads, the formula doesn't work. Okay, so we will use Minitab to do the binomial probability distribution. I just let you know there is a formula out there. Okay, so on this slide, and let me tell you what slide number it is. This is slide 14. This is slide 14 in the PowerPoint. This is the instructions for Minitab. Okay, and we'll walk through this together as we work through the examples in just a minute. Okay, but they're there. The other piece that you need for solving the binomial probability distribution problems is this table that is on slide 15. This table needs to become your BFF. You cannot solve the problems related to the binomial probability distribution without this table. Miss Ralston doesn't even try to solve the binomial probability distribution questions without this table. Print it off, draw it, sketch it off, whatever you need to do. This table needs to be your BFF. A smaller version of this table will need to be on your note sheet for the midterm exam. Okay, and again, what it gives you is it gives you, if you're looking for exactly X successes, at most, fewer than, at least, more than. And it tells you how to interpret or calculate the probabilities based on what you're looking for. I give it to you in words, I give you the symbols, and then I give you how to do it. Make the table your BFF. Okay, so let's jump into, also you may be asked to figure the mean and the standard deviation. Here are the formulas. They're a little bit easier. The mean is the number of trials times the probability of success. The standard deviation is the number of trials times the probability of success times the probability of failure square rooted. And again, those formulas are there. You'll be able to have the formulas on your note sheet for the midterm. You need to know when and how to use them. Okay, so let's dive into some questions. That's usually what students want to see anyways, is how do you work the problems? And we're going to start with this example here. Let me see if I can make it a little bit bigger so you guys can see it good. Okay, so the question reads, about 32% of students participate in a community volunteer program outside of school. If 20 students are randomly selected, find the probability that, and then they're going to give us some questions. In this scenario, the X represents the number of students who participate in a community volunteer program outside of school. The P of X is the probability that they participate in the volunteer program outside of school. Okay, so before we actually start working these problems, let's think through the guidelines for whether or not this is a binomial distribution. Okay, so to be a binomial distribution or binomial experiment, the first one is you have to have a fixed number of trials. Basically, guys, this is like your sample size. So in this scenario, it tells me that if 20 students are selected at random, okay, so my fixed number of trials in this scenario is 20. So I do have a fixed number of trials. The second condition is that you have 2 outcomes. Now, it may not be as obvious to you, maybe, but there are 2 outcomes here, because the one outcome is that they participate in the program. The other outcome is that they do not participate. Those are really the 2 options. So there are 2 outcomes for this particular scenario. They either participate or they do not participate. If they participate, in this case, that is going to be our success. Do not participate is a failure. It also tells me the probability of the success in this problem. Okay, so my P, which is my probability of success, it says 32% participate. So my P is 32%, which we normally will express as a decimal. If my success is 32%, my failure is 1 minus that. So 1 minus the 32% gives me 0.68. So the probability that they do not participate would be 68%. The third piece is that your trials are independent. Now, again, this is when you have to kind of think through the scenario. So let's say, for example, would the fact that Keyshawn participates in a community volunteer program outside of school affect whether or not Nana participates, or whether Disney participates, or whether Allison participates? I don't think so. So my trials are independent, because the fact that one of you participates is not going to affect whether the other one does. The last one is that the P, your probability of success, is constant. Well, here again, they tell me that my probability of success is 32%. Okay, so I have to assume that it's going to remain at 32% throughout the entire problem. So I have met all 4 conditions for being a binomial experiment. Now, it may not literally ask you those questions to verify it, okay? It may indicate that it is a binomial experiment. But again, it helps me to identify those pieces to make sure that I have a binomial experiment. Okay, so one other thing I want us to think about, because we need this information in order to work the problem in Minitab. It says the number of students who participate. Well, we know we're going to go up to 20 students because we're going to select 20. Because what you have to remember is there could be 0 students. So the number of students could be from 0 all the way up to 20. You have to allow for the option that no students volunteer. So you do have to include 0. Okay, so again, they're asking us to find some probabilities, but to find those probabilities, I'm going to need to go out to Minitab to do the calculations. I'm not going to use that crazy formula. Okay, so the first question asked me to find the probability that X equals 15, or that exactly 15 students participate. Okay, but I got to create my distribution first. So I'm going out to Minitab. It's probably gone to sleep, so give it just a minute. It's thinking about it. It's thinking about it some more. Okay, so here's what we do. The first thing we need to do is enter the number of participants who volunteer. Okay, so my column 1, I'm going to put participate in, whoops, I misspelled that. Participate in volunteer program. Okay, you can label it whatever you want. Oops, my name's too long. Okay, I'm just going to put participants. This is my X. Okay, and there's a possibility that I have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Ooh, mercy. I'm making a mess. 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay, I stop at 20 because I know that's the number, total number that I'm going to survey. Make sure I didn't get anything else wonky in here. Okay, so I list out from 0 to the total number in my group, in my sample. Okay. So you have that data entered. Again, I tell you to do that on slide 14. Enter all possible values of X into column 1. Okay, then we're going to go to calculate because I want it to calculate a probability distribution, and we have to choose the correct one. Okay, so I've got my column entered. We're going to go to calculate a probability distribution. We're doing a probability density function. We're going to input a column of values so that it does all of the values at one time. Those values are in column 1. I have to indicate what type distribution I'm doing. We are doing a binomial. Anytype does a bunch of them, but I want the binomial. How many trials did I have? We had 20. The event probability is the probability of success. And the probability of success stated in the problem is 32%. I enter it as a decimal value. And I want it to display a table. I'm going to click OK. And in the top half of the screen, my table appears. And I'm going to copy this table and bring it over to my Word document. And I'm going to put it right here underneath the question. Okay, so see, this tells me I had a binomial with n equal to 20 and my probability of success is 0.32. If we go to slide 15 to look at our table that Miss Ralston says to make your BFF, we're looking for exactly or equal, and it says read results directly from Minitab for X. So I've created my table and I'm looking for X equals 15. So I'm going down the X column till I get to 15. And the value next to 15 is my answer. So the probability that exactly 15 students volunteer is this really, really small number. It's 0.000085. That's the answer. Same scenario, but the next question says, find the probability that at most 14, okay, at most 14. It's the same table that Minitab has already created, but I'm going to read it differently. Again, look at your table. I'm doing at most. At most implies less than or equal. So another way to view this of at 14 students is you have the probability that X is less than or equal to 14. So the table tells me at most, you're going to add the results from Minitab for 0 up to X. So in this scenario, that means I need to add from 0 up to 14. So I'm going to add, I'm going to write it out, probability of 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14, because it could be equal to 14. But guys, I have all those numbers here. I just have to enter them into my calculator. And guys, you need to be extra careful about typing them into your calculator. You may even want to add them twice to make sure you don't make a mistake. So let me see if I can add those together real quick. Woo! Okay. Oh my, I've obviously made a mistake because I got 18,802. Okay, so I've obviously made a mistake because I know that the probability cannot be over 1. Okay, so let me see if I can do it real quick again. Sorry. But at least I know that I've made a mistake. Okay, I get 0.99991. Whew. Okay, again, I knew I made a mistake the first time because I couldn't get a value greater than 1. So my second time, I did better. I will tell you, as a side note, when you're entering these answers into Minitab, or not into Minitab, excuse me, into D2L for your homework, the homework likes you to put what they call the leading 0. Okay, so it likes to see 0 decimal point. Okay, D2L likes to see 0 decimal point and then the decimals after. So be careful as you're entering things into D2L. It likes to have the leading 0. All right, then let's see the next question. Same scenario. It asks us to find the probability of fewer than 8. Fewer than 8. So again, if I go over to my table, and I keep going back to this because that's what I want you guys to do. Okay, fewer than means less than. Okay, it's just less than. So fewer than 8, we would have the probability that X is less than 8. And it tells us to add the results from Minitab or 0, 1, 2, up to x minus 1. Do not include the result for x. X is not included here because it says fewer than. So that means for this problem, I would do 0, 1, 2, 3, 4, 5, 6, and 7. And again, I have those numbers. I'm going to add them up. Okay, I'm going to add up those numbers again very carefully. Maybe not make a mistake this time.
You forgot the 7.
Oh, thank you.
You
Thank
know,
you. Thank you. Thank you. Okay. Okay, so I'm going to add those up. Oh, I got 2 plus signs in there. Okay, so when I get all those added up, 0, 1, 2, 3, 4, 5, 6, 7, add up those probabilities, I get 0.707765. Again, when you're entering it in your homeworks in D2L, it wants you to put that leading 0. Okay, questions. I'm going to do some more examples in a minute, but I want to show you how to calculate the mean and the standard deviation as well. Okay, so using that same scenario where about 32% participate in a community volunteer program, we select 20 students at random, find the average or expected number of students. Okay, so again, they're asking me kind of in a different sort of way to find the mean. Okay, to find the mean, and then it does also ask me to find the standard deviation. It's a formula. The formula for the mean is N times P. Remember, N is the number in your sample, so we're selecting 20, and our probability of success, which is P, is 32%. So that's a whole lot easier to calculate than what we were doing a minute ago. Okay, so 20 times 0.32 gives me a value of 6.4. So on average, about 6 to 7 students are going to participate in a community volunteer program outside of school. The standard deviation. Standard deviation is also a formula. Okay, it is the square root of N times P times Q. Okay, so again, our N is our sample size. We selected 20 students at random. Probability of success was 0.32. I believe we calculated Q earlier and it was 0.68. So I'm going to multiply all of that stuff underneath the square root symbol. So I do 20 times 0.32 times 0.68, which gives me 4.352. Then I'm going to take the square root of that. and I get 2.0861447. Again, normally we would round to two places, so that's going to take us to about 2.09. Questions? I want to do a couple more examples because I want you to have an example of how to do each one of these types. We've done an exactly, we've done an at most, and we've done a fewer than. Okay, so let's see if we can do an example of an at least and a more than. But I'm going to change scenarios on you so we can walk through Minitab again. Okay, it says Danielle takes a 10-question true-false quiz, but did not study and randomly guesses each answer. Find the probability that Danielle, okay, and then they give us some scenarios. But again, before we work through the questions, let's verify that this is a binomial. Again, the first thing about being a binomial is you need a fixed number of trials, and it tells us that she's going to take a 10-question quiz. So there are 10 outcomes. So I'm good on that one. Number two is we have 2 outcomes. It tells us in this problem that she's doing a true-false quiz. So the 2 choices are true or false. So I do have 2 outcomes, so I'm good on that particular requirement, but let's think for a minute. It doesn't really tell us in this problem, it doesn't say, you know, like 32%. Okay, but think about it, it's true false. The probability that she would choose true if she's randomly guessing, there's one way to choose true out of 2. So that's like 50%. So she's got a 50% chance of selecting true, but then also 1 minus that 50%, there's a 50% chance she's going to choose false. So it may not always give you a percentage, but they usually have enough information. Again, if you've got 2 outcomes and they're equally weighted, they're 50-50. Okay, third option is the trials are independent. Well, it says she didn't study and she's randomly guessing. So the fact that she chooses true on the first question is probably not going to affect whether she chooses true or false on the second question. So I would say they're independent. And the last one is that the P is constant. Well, each question is true, false. So her options are not going to change. And again, apparently she's randomly guessing. So it does meet the requirements for being a binomial distribution. So the first question asks us to figure out, you know, if she's randomly guessing, what's the chance she's going to pass the quiz with a grade of 70%, meaning she gets at least 7 out of the 10 correct. Well, before I can do anything else, I've got to go out to Minitab and calculate my distribution. So I'm going to get a clean sheet of paper. Okay. These are her quiz answers. And remember, you have to allow for the option that she gets none of them correct. So she could get 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, or 10, all 10 correct. Make sure you include the 0. Then we calculate. Calculate a probability distribution, probability density function for a column of values, and they are in column 1. We are doing a binomial distribution. We have 10 questions, and there's a 50% chance she's going to get it correct or choose true or false. Okay. And my table appears in the top half of the screen. I'm going to copy it over to my paper so we can talk about it. Okay, it says the probability of at least 7. So at least 7 would be the probability that X is greater than or equal to 7. Again, if you go back to the table, and I keep referring you back to it, look for that phrase, at least, which implies X or more. So it says, add the results from Minitab for X up to N. So the probability of at least 7, we're going to do 7, 8, 9, and 10. Okay, so 7, 8, 9, and 10. So you have the numbers, you're going to have to add them together. So you are going to need your handheld calculator. So I'm going to add those values together, trying to add very carefully. And I get a value of 0.171876. So she only has about a 17% chance of passing the quiz if she is truly guessing. Okay. The next one, and let me get this all on the same page. Okay, says what's the probability she does not pass the quiz, meaning that she gets fewer than 7 correct. Okay, so fewer than 7. Again, in symbols, that's going to be probability that X is less than 7. It doesn't include the 7. Again, if I go back to my table, okay, fewer than, I'm going to add the results for 0, and I do not include the X. So this would be probability of 0, probability of 1, 2, 3, 4, 5, and 6. Again, you do not include the 7. So you go from 6, from 0 to 6. So I would have, if I add those numbers together, I get 0.828124. Again, it's important that you put that leading 0. So there's about an 83% chance, roughly 82.8, that she's going to score less or do not pass the test. Then the last one, at least for this series, says probability she scores 90% or higher, meaning she gets 9 or more correct. So this is actually like X is greater than or equal to 9. Okay, this one is kind of like greater than or equal to. So that would be almost like the at least, because it's X or more. I don't have one that's just a more than. Okay, when you're doing just a more than, remember you're not going to include the X. Okay, so this would be, let me get my little table down here. Okay, for 9 or more, this is going to be 9 and 10. Okay, so I would add those two values together. Which gives me 0.010743. So there's only about a 1% chance that she's going to score 90 or higher, 90% or higher. Okay, let me do one with just a more than. I'm going to make one up. Let's say she scores I'm going to write it a different way instead of it says scores. Let's say she gets okay, so let's say for this example that I just made up, the probability that she gets more than 5 correct. Okay, so this is a more than. So this is going to be a probability that X is greater than 5. And I wanted to do that because that gives us you an example of this last example. For more than, you're going to add the results from Minitab for X plus 1, X plus 2, all the way up to N. Do not include the result for X. So if we're saying more than 5, that would be the probability that she gets 6, 7, 8, 9, or 10 correct. We do not include the 5. Okay, so be careful. You got to really, really, really pay attention to the words. And please use the table. That's why I provided it. You can make a smaller version to have on your note sheet for the midterm, and I strongly suggest that you do that because I know that there are questions related to the binomial on the midterm. This one turns out to be 0.376954. Now we could also figure the mean and the standard deviation. They're not asked for it, but let's see if we can figure out on average, if she's guessing, what would be the mean? Okay, the mean, remember, is N times P. So 10 times the 0.5 would be 5. So on average, we would expect students to get 5 questions correct. The standard deviation. is the square root of N times P times Q. So there were 10 questions, 50% chance she gets it right, 50% chance you get it wrong. Okay, so we would have the square root, get my calculator, 10 times 0.5 times 0.5 is 2.5. And then you're going to square root it. Whoops. Take the square root last. I get 1.58113883. Rounding to two places, you get 1.58. Questions? Okay. That really was today's lesson. I've got 25 minutes. I could begin continuous probability distributions, but since you all had such a struggle because of the access to Minitab related to quiz 2, I'm going to stop there and finish a little early. But do you have, guys, you got quiz 2, which is now due on Wednesday by 11:30 p.m. Your mini project one is due on Friday. If you've started looking at that mini project 1, do you have questions that I can try to answer before we adjourn for the day?
I just got here like 30 minutes ago. How soon will the recording be posted?
It takes it about an hour to process. So I will probably have it posted by at least 2 or 3 o'clock this afternoon.
Okay. That's it. Thank you.
You're welcome. Any other questions related to today's topic or the previous lessons in preparation for quiz 2 and mini project 1?
Can you do like maybe one more example, just real quick?
Of the binomial?
Yes.
Okay.
What's that? Yeah.
Give me just a second to find one and then I'll share my screen, okay?
Okay.
Because I'll have to go out and find one. I think I have some examples. All right, I'll post this this document when I post the videos, because I know that these examples are not in the course. Okay. So I'll share this when I post the documents.
Okay.
Okay, and I'm going to make it bigger where you guys can see it. All right, this question says, the blood type O negative is called the universal donor type because it is the only blood type that may be safely transfused into any person. Therefore, when someone needs a transfusion in an emergency and their blood type cannot be determined, they are given type O negative blood. For this reason, donors with this blood type are crucial to blood banks. Unfortunately, this blood type is fairly rare. According to the Red Cross, only 7% of the U.S. residents have type O negative blood. Assume that a blood bank has recruited 20 donors. Okay. And then there's a series of questions. So it doesn't, the challenge, I suppose, is it doesn't anywhere in this scenario tell you that this is a binomial. So you have to be able to recognize it as a binomial. So as I'm reading through this and thinking through, thinking it, I know it's specifically binomial because that's what you ask for. But again, think about it. We have a fixed number of trials because that last sentence tells us that they're going to recruit 20 donors. The biggest thing to be sure that you have when you're thinking about the binomial is, do you have two outcomes? And again, this is one that might be kind of weird to think about because basically we're saying that they have O negative blood or they do not have it. Now I know there are other blood types besides O. Okay, so there are more options, but we can reduce this problem to those two outcomes. They either have it or they don't. Are the trials independent? I would say yes, because the fact that, say, I have O negative does not affect whether Emmanuel has O negative. So they are independent. And then is the probability constant? We can assume that it is because, again, the Red Cross has identified that only 7% have O negative. So the probability that they have O negative is 7%. Written as a decimal is 0.07. That means the probability they don't is 1 minus P, or 1 minus 0.07, which is 93%. So there's a 93% chance that they don't have O negative. Okay, so it does represent a binomial distribution. And so I've got to go out and calculate it first. And I have 20 donors. Okay, so I'm going to get me a new spreadsheet. And again, in the first column, I'm going to put the number of donors. You have to remember to allow for 0. And then I can have any option, if I can type, up to 20, because we had 20 donors recruited. Sometimes Minitab's a little glitchy, so I'm having to type slow. Okay, make sure I don't type something crazy. Okay, so we've got our number of donors in from 0 to 20. I'm going to calculate. Calculate a probability distribution, probability density function. We're doing a column of values. My values are in column 1. It is a binomial. And guys, right now, that's the only option you have because that's the only one we've talked about. So please make sure you choose binomial. We have 20 trials. The probability they have O negative is 7%. 0.07. And I click OK. And then I'm going to copy the table over to my page. Okay, so the first question says, what is the probability that at least 2 of the donors have type O negative blood? Okay, please refer back to the table. At least implies X or more, and we add the results for X all the way up to N. So for this problem, let me get we want to do the probability that X is greater than or equal to 2. So we're going to do 2, 3, 4, 5, all the way up to 20. Okay, so from 2 all the way down. Okay. So then you want to type those numbers in. And when you get them typed in, you get 0.413143. So about 41%, there's about a 41% chance that at least 2 of the 20 would have O negative blood. Nana, you all right?
Yes.
All right, question 2, and I'm going to move this down so I'll have room, says, what is the probability that fewer than 5? Okay, fewer than 5. Again, it's the same table. We've already created it. I'm using the same table throughout these series of questions. So fewer than 5 is X is less than 5. Okay, again, go back to your table. Fewer than is simply less than. It does not include the result for X. So for this problem, fewer than 5, we would do 0, 1, 2, 3, and 4. We do not include the 5 because it's fewer than 5. So we would add those numbers up. It's going to take me a minute to do that. Okay, so when I add those numbers up, 5 or fewer is 0.989294. Okay, question 3, same scenario. So I've already got the table. It says, what is the probability of exactly 7? So this is the probability that X equals 7. Again, going back to my table. for exactly, it says read directly from Minitab. There's no adding or subtracting. I'm just going to go to 7 and read that number. It is 0.000249. Number 4, same scenario, says what is the probability at most 12 of the donors have type O negative blood. Okay, so let's go back to our table. At most 12. At most means from 0 up to 12. You do include the X. So at most is the probability that X is less than or equal to 12. So you're going to do 0, 1, 2, all the way up to and including 12. And quite honestly, for this scenario, that's going to be 1. What is the probability? The next question, let me scroll down some, get out of the way. What is the probability more than 16? Okay, more than 16. Again, thinking about what that word means, more than, it's going to be the probability of X is greater than 16. Okay, again, think about your table. More than does not include the X. Does not include the X. So this would be probability of 17 plus 18 plus 19 plus 20. And if you look at those numbers, it's 0. Okay, then it asks you to find what is the mean number who have type O negative blood. Okay, remember the mean is N times P. So we have 20 people and there's a 7% chance that they're going to have type O negative blood. It's 1.4. The standard deviation is the square root of N times P times Q. So that's the square root of 20 times 0.07 times 0.93. We figured that earlier. And then I'm going to multiply those together. Okay, so 20 times 0.07 times 0.93 would be the square root of 1.302. So when I square root it, I get 1.141052146. So it would be about 1.14. Honestly, Minitab does the hard part. You just have to know how to interpret this table and what values you need to add together. And then when you're adding them together from the table, you have to be really, really careful, because as you saw, I made a mistake earlier and got it out of whack. Nana, does that help?
Yes, and I was gonna ask how you got the 0.93, but I just saw it where we got it.
Oh, yeah, because it's 1 minus the 7%.
Yes.
Okay, other questions? Emmanuel, do you have any?
No, not at the moment.
Okay, again, it'll take me about an hour or so to get the video processed, and then I'll get it posted up, and I'll post those extra examples I will post into the Zoom folder as well. Anything else I can do for you guys today?
No, that sounds good.
All right, I will see you guys Wednesday then, and we'll continue talking about probability distributions, specifically continuous probability distributions.
Okay,
Thank y'all.
Thank you.
you're welcome.